Okay, I started the recording. Let's today let's talk about trees, which is the one of the simplest graphs that you can imagine. So what is a tree? It's just a connected graph. What is a tree? Let's recall the definition. A connected graph with no paths, with no cycles. Okay, so it's a tree. There are some very simple facts. For example, given a tree, let me say, given a tree, first of all, the edge number of the tree is the vertex number of the tree minus 1. So you can imagine a path. So let's draw a path. So you have 4 vertices and 3 edges. So clearly the edge number is the vertex number minus 1. Okay? And it's true for all trees. Okay, maybe do you think it requires a proof? I think the simplest proof is just induction. This is true for all trees with, for example, with a vertex number smaller or equal than k. And if the vertex number of the tree is k plus 1, and then you delete a leaf, you delete one vertex. And if you delete a leaf, then automatically you delete a edge. Right? What we call a pendant edge. Okay, which is the edge, which is the edge that is incidental with the leaf, and then you get a tree with smaller number of vertices. Okay, so and you have deleted one edge and one vertex. So by induction, conclude that the edge number is always the vertex number minus 1. Now let's see another property. In a tree, every vertex, every edge is a bridge, is a cutward edge, is a cut edge. For example, I draw a tree somewhere like this, and this edge, for example, it must be a cut edge. It disconnected 2 parts. Okay. So it disconnected disconnects the graph, the tree into 2 parts. 3, a tree plus any edge plus any edge. So a tree, any tree, if a t plus any edge, I mean you do not add new vertices. You add one edge. It contain a unique cycle. So it contains exactly one cycle. This cycle contains this edge you added. So if you draw the picture, it's something like if you have a tree like this, something like this, and here, originally there is no edge. If you draw this edge, then you create a cycle, and exactly the cycle is unique. This edge E must belong to a unique cycle. So this requires a proof, really. That's proof 3. Proof of 3. So consider 2 vertices U and W. U and W. Let's say here, if without this edge, I can see V and W. Such that VW is a non-edge, is not an edge. So what I want to do is that I want to add this edge into the graph, and I want to show that there is a cycle. So before, since it's not an edge, I claim that there is a unique tree, a path joining V and W in the tree. So for example, in this picture, I have this. So if I draw red, I have this. Okay, this is a unique path joining V and W. And it's always true. There is always a unique path joining V and W if VW is not an edge. Because why is this true? Because if you have find two different paths, then you can argue, you can find some cycle somewhere. Okay? Because two different paths give a cycle, and the tree has no cycle. Okay, so if you have, for example, you can think about this. It's not a complete argument, but it's pretty clear. Okay. So, for example, you call this path P, then clearly T plus UV contains a cycle which is just a P with UV. So you have P connecting U and V and plus this edge UV. So it's a cycle. Okay? And this cycle clearly is unique. Any questions? Okay. So I think it's pretty clear. But about trees today, in the second part, I will prove something pretty nice, I think. But at the beginning, there are some very intuitive definitions. So next, we want to talk about what's called spanning tree. Okay. So but before that, let's look at any connected graph. Given a graph G, a connected graph G. For example, it has n vertices, and it's connected, and we don't know it has a cycle or not. If it doesn't have a cycle, it's a tree already. So if it has cycle, we don't call it a tree. It's not a tree. So whenever we find a cycle, for each cycle in G, we delete one edge. This is a pretty arbitrary. So you look at the graph and you find one cycle and you take one edge and delete it. And then you still call the graph G, for example. This is a pretty standard thing to do. So you update the graph G into something else, but there will be too many notation, too complicated. So you still call this graph G after you delete this edge. And then you look at the new graph G and you ask if there is a cycle again. If there is a cycle, you find it and delete it again until you cannot do it anymore. Okay? Delete cycle and then repeat until the graph has no cycles. You stop. When you stop the graph, since the graph has no cycles, you stop with a tree, and we call the final graph a spanning tree. It's a little too complicated. Actually, we have another way to define spanning tree. Spanning tree is just, first of all, it's a tree, and then its vertex set is the same with the vertex set of G. So a spanning tree is just let me say, or alternatively, you can define or equivalently, a spanning tree has the same vertex set with G and is a tree. So spanning tree is a tree with exactly the same vertex set with G. Okay. So I think ask some questions. For example, what is let me put v is the vertex number of G. Okay, so the number of edges in a spanning tree is what? I'm waiting for an answer here. People, so remember, spanning tree is a tree. So what is the edge number of the tree? So since the vertex number is v, and the spanning tree has the same number of vertices with G, so the edge number is v minus 1. Okay, so in this case, we also call this number the so-called cut set rank. For some reason, we probably will explain in later lectures. This number is called cut set rank. And what is the number deleted in the above process? The number of edges deleted in the above process. So originally, suppose the edge M is the number of edges of G. So we have to keep deleting edges until the total number of edges arrive at v minus 1. So remember this. So the total number of edges deleted in the above process is m minus v plus 1. And this number we call the cycle rank. Okay? So it's now you see something called rank, and it is related to some rank of certain matrices. So I make a survey about if you guys has already learned linear algebra, and I got positive answers all over. So I think I will go into algebraic graph theory for several lectures starting from the next. Okay. So now we have enough definitions. Let me see a proposition. So 1, T is a spanning tree of a connected graph G, then for any E edge from EG minus ET, which means that E is the one edge that we have deleted at some point. So it does not belong to EG, does not belong to ET, does not belong to this spanning tree, but it's one of the edges in the graph G. Then there is a cycle. For example, I call CE in G. So this I have already proved. Okay, so I have proven this earlier. So for any edge, non-edge, if you add it, you will create a cycle. And here, remember, we have how many possibilities of this kind of edge? There are exactly m minus v plus 1. So each one of them will create a cycle. So you have a bunch of cycles, and these cycles will be a basis of some subspace in your linear algebra language. And the second part, which is very similar for any edge E in the spanning tree. In this case, there is an edge cut so edge cut of the graph G, which intersect T in E. So there is a edge cut, which is a set of edges, and this edge cut intersection with the graph tree T is exactly E. So what happens is that this I leave as an exercise for this week. So but before you do it, let me draw a picture. So let me say here I got a tree. Okay, so but this is my tree, spanning tree, and originally probably the graph has some other edges. For example, here I got edge, here I got edge. I don't know, this have edge. Okay, this is the red edges. I deleted them, and the remaining black edges form a tree. Okay, so I got tree, and here this is the red edges I deleted. So now for any black edge, E. So clearly, if I delete E, I can split the tree into two connected subtrees. And if I look all the edges, including red edges, connecting the two parts, E is one of them. And this also is one of the edges which connecting two parts. And this is also. So for example, I call this F1, F2, and F3. Then E, let me write E, F1, F2, F3 is actually an edge cut, and the intersection of this with T is equal to exactly E. So this is the conclusion. So for any E you choose, there exists actually, or again, unique edge cut of the graph G. This edge cut intersect T at the edge E. Okay, so the proof is you can think of it later. Okay, so it's actually very parallel to the proof of the first part. Okay, in fact, all these cycles, they are called a fundamental set of cycles associated to the spanning tree T. And the collection of all the cut set above is called a fundamental set of cut sets associated with T. Enough all for the propositions. Let me see a problem. Let's solve a problem. So let's say there are 3 airlines. Let's say here in Brazil, let's say we have Azul, Gol, Latam, okay, and Azul. Now, suppose we have 15 cities. And we require, so we ask the following. We require that if one of the companies is stopped, if one airline has stopped its service, so there is no, for example, Go for some reason does not operate, then people still can fly from any other city to any other city, to any city to any other city, from between any two cities. Then the question is, how many airlines in fly routes in total, at least? So the question is, there are at least how many flight routes? I mean, how many flights from one city to another? So this is really a problem about trees. So for example, I got a graph on 15 vertices. And how many edges do I need to make this graph connected? So the solution is 14. I need 14 edges to make this graph connected. Okay? So let's say A1, A2, A3 is the number of flight routes provided by the airlines, by each airlines, by all these, by each airlines respectively. Okay, so what this observation told us? If I stop A3, for example, I stop Azul, I don't know, stop one service, I need this to be at least 14, because otherwise I cannot use 13 routes to connect all cities, but I can do it with 14. And the same thing happens for A1 plus A3, and also A2 plus A3 is greater or equal than 14. Okay, so altogether gives you 2 times A1 plus A2 plus A3, at least 42. And it means that A1 plus A2 plus A3 is at least 21. Okay, this is my solution. So I at least need 22 different flight routes in total. Okay, this is my question. There are at least how many flight routes? The answer is 21. Okay? Okay. So this is already concluded with our very basic notions about trees and some basic properties. So let's take some rest. I'll stop here, and let me stop the recording.